8.2 now is the second part to what we started discussing 8.1. So in 8.1, we saw that we would sometimes need to compute probabilities involving the mean of a sample of several observations. In a similar way, we sometimes need to compute probabilities involving the proportion of individuals in a sample who have some characteristics. So in other words, we want to be able to compute probabilities involving proportions. And that's what the topic of discussion is in 8.2. Now, what do we mean by proportion? This is a word that I think I've probably thrown around a couple times this semester, but we haven't ever bothered actually talking about what a proportion is. So what I want to do is relate it back to the binomial distribution, okay? So proportions are related to the binomial distribution because we can consider an individual who has the characteristic in question to be a success, and an individual who doesn't have the characteristic in question to be a failure. So the population proportion is the same as the probability of success, P, in a binomial experiment. Meanwhile, the sample proportion, P hat, is the same as the relative frequency with which success occurred, right? The sample proportion, P hat, is used to estimate the population proportion, P. And in this section, we're going to be computing probabilities involving P hat, okay? First of all, let's just do an example showing us how to calculate just P hat itself. It's not a difficult thing, but I just want to make sure we're all on the same page. So this first one says, Opinion Dynamics Corporation conducted a survey of 1,000 adult Americans aged 18 or older and asked, are you currently on some form of low carbohydrate diet? Of those surveyed, 150 said they were. Find the sample proportion of individuals surveyed who were on a low-carb diet. Okay, so the sample proportion is the number of successes, X, divided by the number of observations, or in other words, your sample size, N. Number of successes, so the characteristic in question is whether or not they're on a low-carb diet, and 150 of them said they were, right? So 150 successes out of 1,000 observations. Being on a low-carb diet is not successful in my opinion. And I say that as a diabetic. No, okay, if you're on a low-carb diet, that's fine. Anyway, 150 out of 1,000. So you do that calculation, you get 0.15, and there's the sample proportion. So these are the things that we're talking about, right? We're talking about sample proportions, and we want to see, like, given some scenario, what's the probability that the sample proportion is greater than 0.2 or is between 0.13 and 0.17 or whatever, right? Okay. Now, just like with the sample mean, the sample proportion is likely to differ from one sample to the next, right? Like in this particular sample, 150 people said that they were on a low-carb diet, but if you went out and surveyed a different set of 1,000 people, probably you might get a different number here. You might get like 149 or maybe 152 or something like that, right? So P hat is not going to be the same from one sample to the next. It's probably going to be different for each sample that you look at. So just like the sample mean, we can treat the sample proportion P hat like a random variable, and in which case we would like to get a handle on what its shape, center, and spread are. And here are the results of that. Again, I'll explain where these results come from later on in the section. Okay, but for now, just take my word for it, and I'll run you through a couple example problems so that you understand what's going on. But here's the idea, right? The center of the distribution, right? The mean of the sample proportions, mu sub P hat, that's equal to P. The standard deviation of the sample proportions, sigma sub P hat, that's equal to square root of P times Q times N, where Q is 1 minus P, right? Q is the probability of failure. And then the shape of the distribution. Now here's something that's really pretty amazing to me. Shape of the distribution of P hat is normally distributed. It's also normally distributed, which is just crazy because you're starting with this binomial distribution, and yet when you look at the distribution of the sample proportions, you get a normal distribution. You get this bell-shaped distribution, which is just kind of crazy. But these are the conditions that have to be met in order for you to conclude that the distribution is normally distributed, right? So your sample size needs to be less than 5% of your population size, and n times p times q needs to be bigger than or equal to 10. So let me just give you a couple examples. Right, so this first one says, describe the sampling distribution of p hat if p equals 0.76, n equals 60, and capital N equals 1 million. Okay, when they say to describe the sampling distribution, they're asking you to describe the shape, center, and spread of the distribution. So as far as the shape is concerned, we know from the results on the previous page that the shape is going to be normally distributed, provided that those two conditions are met. And again, those conditions were our sample size needs to be less than or equal to 5% of our population size, right? So that's condition 1. Okay, so we want to know if this is true. And then the other condition is that n times p times q needs to be bigger than or equal to 10. So we want to test both of those. So to test the first one, our sample size was 60, and our population size was 1 million. Okay, I'm pretty sure that this is pretty safe to say, right? Like 5% of 100 would be 5, so 5% of 1,000,000 would be 1, 2, 3, 4, so 5,000, 50,000, 50,000. Okay. Yeah, 60 is definitely less than 50,000. So that condition is met. N times P times Q needs to be bigger than or equal to 10. So let's see, 60 times 0.76 times Q. Well, if P is 0.76, then Q is 1 minus 0.76 is 0.24, right? So if Q is 0.76, or sorry, if P is 0.76, then Q is 0.24. We want to know if this is bigger than or equal to 10. Let's see. 60 times 0.76 times 0.24 is about 10.9. So say it's about 10.9. It's definitely bigger than 10 though, so that condition is also met. Since those two conditions are met, we can say that the shape is normally distributed. So p hat is normally distributed. Okay, so p hat is normally distributed. So there's that. There's the shape. In other words, if you were to go out and collect all of the possible sample proportions and then make a histogram out of all of the sample proportions, that histogram would have a bell shape. And I'll show you this when we look at some simulations in a second. Okay, but the shape is normally distributed. The center, mu sub p hat, well, that turns out to be the same thing as the population proportion, which is just 0.76. So there's the center of the distribution. That should make some intuitive sense, right? Like if you looked at all of the different sample proportions and then you took the average of those sample proportions, you're going to get the population proportion, of course, right? To use this concrete example, it's like if the population proportion is 0.76, then if you go out and collect a sample, your sample proportion is probably going to be close to 0.76. It might not be exactly 0.76, but it'll be something close. So if you looked at the list of sample proportions, you might have gotten like 0.74, and then 0.79, and then 0.75, and then 0.73, and then 0.76, and then 0.78, and whatever, right? And if this is your list of sample proportions, now if you take the average of these, you're going to get your population proportion, 0.76, right? So there's the center, and that fact should make some intuitive sense. Now the spread, this one makes a little bit less intuitive sense, at least to me. But the spread, sigma sub p hat, is equal to the square root of p times q divided by n. Okay, so that's going to be the square root of 0.76 times 0.24 divided by 60, right? Divided by 60. square root 0.76 times 0.24 divided by 60 is, let's go 3 decimal places, 0.055. Right, so there's the spread. Okay, so that's it, right? There's the shape, center, and spread of the distribution. So that's one type of homework problem you might encounter. More commonly, you're going to run into problems like this. It says, according to the National Center for Health Statistics, 15% of all Americans have hearing trouble. In a random sample of 120 Americans, what is the probability that at most 12% have hearing trouble? Okay. Well, so in order to compute this probability, we need to be sure that p hat is normally distributed first. So the conditions that we have to check are that, first of all, our sample size has to be less than or equal to 5% of our population size. Our population size in this case is Americans, right? That's the population in question. And there are like 300 million of us, right? I'm pretty sure that 120 is less than 5% of 300 million, okay? So I'm not gonna bother to write that down. That's almost certain to be true. The other condition that we have to check, n times p times q bigger than or equal to 10. Now that condition is a little bit more likely to fail. So just checking that one real quick, let's be sure, right? We need to be sure n times p times q is bigger than or equal to 10. So sample size is 120. Proportion is 0.15. So probability of failure is 0.85. We want to know if that's bigger than or equal to 10. Let's see, 120 times 0.15 times 0.85 is 15.3. That is bigger than or equal to 10 for sure. So we know that p hat is normally distributed. And so consequently, we can use the normal calculator to compute this probability, right? We're going to go to stat, calculators, normal. When we get there, we're going to have to enter something for the mean, right? What we want to enter for the mean is mu sub p hat, right? Which is equal to the population proportion of 0.15. When we enter something for the standard deviation, we're going to enter sigma sub p hat. That's the same thing as sigma divided by square root of n. Okay, so that's, I'm sorry. Look at me making a huge mistake. No, that's the wrong formula, right? For sigma sub p hat, we want to do the square root of p times q divided by n. My apologies. Yeah, square root of p times q divided by n. So this is going to be the square root of 0.15 times 0.85 divided by 120. Let's see. That's equal to 0.033 approximately. And now let's compute the probability they're asking us for. They're looking for what's the probability that at most 12% have hearing trouble. So we want to compute the probability that p hat is at most 12%. At most. So that means that p hat could be less than 12% or equal to 12%, but it can't be more than 12%, right? It has to be less than or equal to 12%, right? Probability that p hat is at most 12%. Okay, let's see what we get. So I'm going to go stat, calculators, normal. We want the mean to be 0.15. We want the standard deviation to be 0.033. And we're looking for the probability p hat is less than or equal to 0.12. Okay, so that comes out to about 0.1817. Okay, and that's that, right? So that's how that thing works. Right, just like we did when we were looking at probabilities involving the sample mean, we can use this kind of stuff to perform inference, right? So doing these kinds of calculations are important when it comes to performing inference. And here's an example of that. It says, suppose that a random sample of 120 Americans who regularly listen to music using headphones results in 26 having hearing trouble. What might you conclude? Okay. Well, first of all, I guess to get a handle on this, we should figure out what 26 is as a percentage, right? Like what proportion here ended up having hearing trouble. So p hat in this case would be 26 out of the 120 American surveyed, right? And that's about 0.217 if I round to 3 decimal places. So 21.7% of the people in this survey had hearing trouble. That does seem a little bit strange given the fact that only 15% of the population in general has hearing trouble. So what's different about this sample of people versus the general population? Well, this sample of people, it says regularly listen to music using headphones, right? So what conclusion we might draw from this is that listening to music using headphones damages your hearing, right? Go figure. It's not a surprising result, but that's what we would conclude. Now, here's the caveat, right? We really can only conclude this if this is truly a strange result. And to see if it's truly a strange result, we should compute the probability that we would get this proportion, right? In other words, we want to compute the probability that our sample proportion would be at least as large as what we observed, okay? So we want to be able to compute this probability. If it's really small, like if there's a really small chance that this would happen, then the fact that it did happen tells us that listening to music using headphones is a bad idea for your hearing, right? So let's see if we can compute this probability. Now, to compute this probability, we're going to go to Stat, Calculators, Normal. For the mean, we're going to put in mu sub p hat. For the standard deviation, we're going to put in we're going to put in sigma sub p hat, which is equal to square root of pq over n. And we actually already did this, right? We did this up here. So I'm just going to steal my answer from the previous part and say that, this is approximately 0.033. And so now probability that p hat greater than or equal to 0.217, let's see what we get. So we already have the mean at 0.15 and the standard deviation at 0.033 like we want. We're going to change this to greater than or equal to 0.217. And there's that probability. So 0.0212. In other words, there's only a 2% chance that we would have obtained a sample with a sample proportion of 21.7 unless there was something strange about the sample. And there was, right? This particular sample of people regularly listen to music using headphones. So what might we conclude? We conclude that listening to music using headphones results in hearing trouble. Okay, so there's that. All right. So that's the idea there. Just like in the previous section in 8.1, you could probably stop the video here and have a fairly decent shot of doing well on the homework problems just by following along in these examples that we've looked at together. But I want to give you some justification for these formulas that we came up with on the first page, and for the idea that the distribution of the sample proportion is normally distributed, right? So, so the rest of this section is just for your benefit, right? To convince you that the stuff I'm telling you really is true. So let's do what we did in the previous section and run some simulations, and we'll look at various different sample sizes to see what happens to the shape, center, and spread of the distribution. So, so I'm going to take you to StatCrunch and run some simulations. So I'm going to go to applets, and then again, you don't have to follow along with this unless you want to. But I'm going to go to applets and then sampling distributions, and this time, so when we did this in 8.1, we did one where we did a bell-shaped distribution and a right skewed distribution. This time we're going to do a binary distribution because we're starting with a binomial variable, right? Like in this example that we're looking at, it says 76% of Americans believe that the state of moral values in the US is getting worse. So it's a binomial problem because either you believe the state of moral values is getting worse or you don't, right? And it says 76% of them believe that it is, so the probability of success here is 0.76. So here's our little simulation. And for part A, we want to simulate collecting a sample of size 10. So if I collect one sample of size 10, here it's going to run the simulation of collecting that sample, and then it's going to compute the sample proportion, right? And there's the sample proportion. So I can do this again, and I'm going to get probably a different sample proportion than what I got the first time, right? And I could do this again and again and again. And each time I'm going to get a different sample proportion than I did, right? If I do this 1,000 times, then this is what the distribution ends up looking like, okay? In fact, I could do this a bunch more times. Now, what you'll see is that this distribution is skewed left, right? You've got this little tail creeping up here on the left-hand side. So this is not a bell-shaped distribution. And so you might be thinking, Mr. Haywood, you lied to us. You lied to us. You said that the distribution would be normally distributed. Well, I said that the distribution would be normally distributed under certain conditions, right? And in particular, right, the sample size needs to be just right. It needs to be less than 5% of your population size, but it also needs to be large enough so that n times p times q is bigger than or equal to 10. And in this case, that's not going to happen, right? Because your sample size is only 10 to begin with. So as soon as you multiply by 0.76, you're already less than 10, right? That's why we're not getting a bell-shaped distribution here. But notice that the mean of these sample proportions is about 0.76, which is the same as the population proportion we started with. And the standard deviation of the sample proportions, well, it's a little bit more difficult to see what's going on there. But if you were to multiply square root of 0.76 times 0.14 and then divide by 10, you know, and take the square root of that, then you would get 0.1. You would get something close to. I'm curious now, but you would get something close to that standard deviation. Let's see. Square root of 0.76 times 0.14 divided by 10 is 0.1032. So it's off by a little, but actually that is kind of a big error. That's kind of interesting. Oh, it's because it's not 0.14. It should be 0.24. Let me see. Yeah, sorry. It should be 0.76 times 0.24 divided by 10. And then you get 0.1351. So that's pretty close, right? Anyway, So that's with a sample of size 10. Let's look at a sample of size 25. So for a sample of size 25, I could keep doing this, and I get these. I get this distribution that starts showing up. But I do it 1,000 times. Well, now I'm getting something that looks a little bit more bell-shaped. There is a slight tail kind of creeping up here. So there's a little bit of a tail. I would say the shape of the distribution here looks like it's almost normal, but maybe it's still slightly skewed left. But it is almost a normal distribution for sure. The mean of the sample proportions is still pretty close to the population proportion, right? So mu sub p hat is approximately the same thing as p. And then sigma sub p hat, right? It should again be 0.76 times 0.24 divided by 25, and then take the square root, right? And you should get 0.0863 or something close to 0.0863. One more simulation. Let's simulate taking samples of size 60. So if I do one sample of size 60, there's my proportion, there's my sample proportion. If I do it again, I get another sample proportion, again, again, and again. And if I take the average of those sample proportions, well, right now it's not looking really pretty close to this at all, but then I've only taken 5 samples, right? If I kept doing it over and over and over again, I'm gonna get closer. If I do it 1,000 times, there we go, right? And again, my standard deviation decreased because my sample size increased, right? And I'm dividing by my sample size, so it makes sense that the standard deviation is getting smaller. Notice the shape of the distribution as well. It's almost perfectly bell-shaped. You don't have any tails going on anymore, right? This is definitely normally distributed. So, so that's the idea there. Hopefully that convinces you that the stuff that that we went over on the first page, right? That these results really are correct, right? Hopefully that simulation convinces you. And that's all I have for this section. I'm not giving you as many examples as I did in 8.1 because I kind of figured that after seeing all those examples in 8.1, 8.2 should come a little bit easier, right? Like the concept should feel a little easier. But there's your homework assignment for that section, and we will see you in chapter 9.